I've been thinking a lot lately about how climate science differs from economics, and in particular how it differs from econometrics. And I keep reading stories about the idea that the climate scientists have these gigantic computer simulation models that they keep running over and over again, which generate predictions. And these computer models are, in fact, very complex. Indeed, they are so complex that they are not understandable even by mere mortals. I have a little bit of background in computer simulation, and I've actually done some things in my career as an economist working with simulation models. And one of the problems with any sort of computer simulation model that you can come up with is that the code that basically controls the functions of the model can in fact get very, very complicated. And if you want to be able to figure out what a model is doing, you almost have to be able to read the raw code in the model. Otherwise, you're stuck just putting inputs into the model and then reading the outputs that it generates without really understanding or knowing what's going on in terms of the actual equations that comprise the model. So I thought that a good way of illustrating this for all of you would be to show a climate change model that simply consists of a black box. And it's a black box that I'm going to write some white text in here if I'm lucky. Let's see how I did here. Yeah, that looks pretty good. What I want to convey to you is the notion that when you have a black box computer simulation, you don't really worry about what's going on inside the black box. You let the people that wrote the code for the thing worry about that sort of thing. And if you want to get bogged down in the details of the code, you can, but you're going to have to be pretty good in terms of reading all of the relationships. This is a standard problem in information technology where you've got some giant program that does stuff, and the only person that really understands what that stuff is that this giant program does is the one that actually wrote the individual statements or equations for the computer. Now, let's think about where all of our other information, let's say if we want to go back here, let me see if I can do this. We'll copy that figure, and then maybe if we're lucky, we'll paste that into our diagram here. That worked pretty well actually. I want to make that a little bit smaller and then drag it down. And what happens then, and I'm going to have to change my color here, but I can actually say that this is an example of input data. And you'll notice that I just simply took the graph of the data that I got straight off of the Wood for Trees website and said, okay, this is one item of information that a climate change model might make use of, and that's as input data the historical record of temperature. And I suppose we could do the same thing if we wanted to. We could copy and paste onto our screen here the carbon dioxide data and all of that other good stuff. Okay? Keep in mind also in this world that if you're doing a computer simulation model, you're moving a little bit away from a standard econometric technique for doing out-of-sample forecasts, but you're asking the equations that are contained in the black box to do those calculations for you. So I'm not showing my curves here that I showed you earlier that extend out of sample. I'm presuming that that's all happening in the climate change model itself. Okay, so let's now add some lines here and basically say, okay, there's got to be some sort of connection between the input data and the starting point in which the climate change model works. And that input data then becomes the starting point for the equations within the climate change model to work, along with some other things, of course. And we can't forget that there's probably a whole bunch of different categories of items that are being incorporated into that climate change model. But an important part of any climate change model would be the historical data. So I can draw a line here between my input data, my climate change model, and what comes out the other end here. And let me illustrate that this way. Let's make a big fat green box. Let's see if we can do this here. Let's make that solid green if we can. I'm going to just do something like this. Cool. This then, whoop, turned it red. Didn't want to do that. Okay, we'll get out of there. Then we'll add outcomes. The outcomes consist of the calculations that the climate change model thought were useful and interesting based on the input data, which is a matter of historical record. Now, it's at this outcome stage then where all of the discussion takes place, because basically what the climate change scientists are saying is that if we do this, our climate change model is going to generate outcomes that are dire. Let's represent that, huh? What fun. Let's go back to a red here and say dire. What's an example of a dire outcome? Okay, the sea level is going to rise, Antarctica is going to melt, polar bears will run out of food, and so on down the line. All sorts of things that I basically call stuff that should cause you to panic. But before you panic completely, remember that whatever is going on inside this black box climate change, what I would call a simulation, can be no better than the quality of the input data that lies in the historical record. So if the input data is bad, there's no way that the simulation model can possibly generate accurate amounts of values. And to the extent that we are simulating events that are going to occur further out into the future, the accuracy of whatever this climate change model thinks it's doing is going to decline. So, where do we come out on all of this? Well, one of the places that we come out on this, and watch the trick I do here, this is going to be fun to see if I can pull it off, but I want to create some policymakers. And we'll make some purple policymakers here. Let's see, that looks good, except that we're not in text mode here. There we go. Let's call policymaker P1, then let's pop down here and call policymaker P2. Oh, lost her again. We'll get her back. Now, the policymakers could be presidents, members of Congress, international leaders of various sorts, all of which think that they are big wheels in the cog because they make decisions. And presumably, they're making decisions based on all these dire consequences that were predicted in the outputs from this climate change model. Wow. We've just seen some of that, right? We've had this big event in Paris where all of these policymakers got together and said, we've got to do something. But keep in mind, number one, policymakers are not computer modelers. They try to base decisions only on the basis of outcomes. And if the climate scientists get together and say, well, this is going to be dire, the Arctic will melt, the sea level is going to rise in California and in Florida, polar bears are going to die, all sorts of things, we need to compel the policymakers to act. How are they going to act? Well, they're not going to sit down and start rewriting the simulation code, that's for sure. They're going to basically say, what were the inputs that went into this model that led to these dire consequences? And the inputs that led into this model, it seems to me, are pretty much the ones that we've been looking at over the last two videos. If, in fact, the historical record indicates something other than a rapidly rising carbon dioxide level thought to be attributed to increased burning of fossil fuels, which in itself is hypothetical. We don't know that as a fact. We assume that that must be the cause, but in this natural science world of studying problems, what happens basically is that the winning theory is the one that has the fewest objections to it. And for the moment, the argument that it must be fossil fuel burning that's causing the rise in the Mauna Loa carbon dioxide level is the theory that seems to have the least amount of debate over. Never mind that there could still be other things out there, researchable things, that could be causing temperatures to increase globally, or, as of current, perhaps not increasing globally. The climate change model can do nothing in the equations to repair issues with the historical record. If there are issues with the historical data, there are issues with the historical data, period. And no amount of computer simulation is going to be able to repair that. So whatever outcomes you see over here are as much a consequence of the data in the historical record as they are in terms of this black box that represents the simulation model. Now the question is, do these policymakers act, or are they just in a situation where we all need to be patient because the historical record indicates that the global temperature is stable now and may start to decline soon, and all of these efforts to get people to cut back on the use of fossil fuels may be for naught, because that's not really what's underlying the system in the first place. It's tough to say that these climate scientists that are versed in the computer code of the simulation model don't know what they're talking about. But my reaction to all of this is that it would be helpful if a few climate scientists knew two other sciences very well. One of them is, of course, my personal favorite, called econometrics, and fitting of lines to historical data and making forecasts to those lines. And the second thing that I think is being missed in all of this is that most climate scientists seem to be only vaguely aware of the role that plants play in the carbon cycle. This drives me bananas at times, and I'm going to end my video right here and let you just simply think about all of this.